A partition of a number is the number of ways you can break that number into a sum of smaller parts. But what if you just want to look at the number of partitions with a certain number of parts in the sum? What about restricting the size of the largest part? Let's first look at how we can make a formula for the restriction on the number of parts. To get an intuition for partitions with restrictions, we'll look at the partitions of 6 with 3 parts. First, we can write out the partitions of 6 that fit the restriction to look for patterns. One that exists is that a couple have a 1 in their sums. To figure out an expression for this group, we can ignore the 1 and look for the number of ways to partition 5 with a restriction of 2 parts. Generally, this is the partition of n-1 with a restriction of k-1 parts. This is what's called a recursive formula because you first must solve smaller versions of it, but I'll come back to this later. The remaining partition that doesn't have a 1 in it can also be turned into a recursive formula of the partition n-k with restriction k. This is because this formula is the same, just that all the parts are decreased by 1, thus minus k because there are k parts. Subtracting 1 from all parts doesn't change how many partitions there are. And there we have it, all groups in the partition are accounted for, and the answer is just the sum of the two, giving us the formula. The partition of n with a restriction of k is equal to the partition of n-1 with a restriction of k-1, plus the partition of n-k with a restriction of k. This is where I'd like to come back to the fact that this is a recursive formula. Right now, it can't solve anything because the calculation will go on forever. This means we need to find certain partitions so we can logically determine the value of at which point to stop the recursion. To find these, let's try running through the calculation of the example we've been using. By the second iteration, we have two of our stopping partitions, p of 4 and 1, and p of 0 and 3. The partition of any number with a restriction of 1 is always 1, because there's only one way to write a number as itself. Thus p of 4 and 1 is 1. The next stopping partition we have is p of 0 and 3, which is equal to 0 because it's a partition of 0 which can't be broken down. The final rule is the partition of 1 with any restriction greater than 1, which equals 0 because 1 is only made of one part. So it doesn't make any sense to ask how many ways to write 1 with 2 parts. And there we go. Using the rules to finish the calculation, we get 3, which is the same as we did when we did it visually. Now that we have a formula for the partition of a number with a restriction on the number of parts, let's try the restriction I mentioned at the beginning, partitions with a specific size. Like with restrictions on the number of parts, we can look at all the partitions of 6 with the largest part size of 3. And again, there are several that have a 1 in their parts. If we take 1 off of the largest part, we get the partitions of 5 with a restriction of 2, which generally is p of n-1 and k-1. But wait, this is sounding a lot like the formula we got before, and as it turns out, the two types of restrictions have the same formula. Isn't this cool? At the start, we had two different ways of restricting a partition, which turned out to be the same in some way. But why? There must be some hidden connection we're missing. To find this connection, I'm going to introduce a new way of representing partitions called Forest diagrams. They use dots to show the units of a number, and each part is on a new row. Let's start by writing out all the diagrams for the partitions of 6 with each restriction. If we look at them for a while, we may eventually notice that the diagrams pair up with one another, just rotated 90 degrees. And this makes sense. When we rotate 90 degrees, the longest row becomes the start of each row in the rotation, meaning the number of rows matches the size of the largest part. And there we have it. The two types of restrictions have the same formula because they're just rotations of each other. And this is one of the reasons I love math. Things that seem totally different turn out to be connected in very interesting ways when you dig a little deeper.